see. So we have this triangular region, well, so for which we're going to find the domain and the range. So let's recall, first of all, that in order to get the domain of a function, we need, or what we do is scan the graph from left to right, and for the range, we scan the graph from bottom to top. All right. So in this case, if it works for you, use these vertical dash lines for to delimit our minimum x and our maximum x. That's what we will do for every single for every single kind of graph. All right. And then let's see for the domain, we can see that's going to be using interval notation. If we look for the smallest value of x, doesn't that look like a -3? And goes all the way to the maximum value of x of +3. And well, in this case, using interval notation, brackets for both. That's because in this case we have inclusive, there's solid points in this case. All right, and well, that's going to be in using interval notation. Now using set builder notation, we use what we did last time for, okay, set x such that x in this case is greater than -3 and smaller than +3. All right, that we did a bunch of practice on converting interval notations with interval notation to inequality form and vice versa. Yes, question?
Is that so -33, is that interval notation?
Yes, this one is interval notation and this one is the set builder notation. Yep. Okay, was anybody absent last time that didn't get these handouts, by the way? Okay. I have a bunch of extras here. Let me give you all of them. What's your name? Okay. Oh yes, you emailed me. Okay, so this is one. This is another one. I have a bunch for you. That's another one, and that's another one. Is that intro? Okay, did I give you a duplicate? No, that's fine. Okay. All right. So let's see. So that's as far as the domain goes. Now let's go about the range for this graph. And Carla, we're looking at we're on page 3 for that handout with the graphs. Okay, so let's scan the graph from bottom to top. And again, what we do is identify the lowest value of y on the graph all the way up to the highest value. That is the lowest, the highest. All right, and well, so we can see the lowest value equals to, okay, range, and the range is going to go between -2 all the way up to 4, and we're using set builder notation. In this case, it's not x, it's in this case the variable y this time, y, such that in this case goes between -2 and 4, and all we do is put the x in the middle and the inequality symbols with both including the endpoints, because again we have solid points. I can't do the curly brace to that. There you go.
We're doing your y limit?
Oh yes. And I mean, sometimes I will do it. I will do it without noticing. Sometimes I will do it on purpose. This time, well. Okay. But the question is now, function or not a function?
No.
Not a function, right? Vertical line test. The vertical line crosses at more than one point. And again, you could argue that at this cusp right here, it's only crossing at one point, and I agree. That'll be, you guys will be right about it. However, we're considering the entire domain or the entire graph as a whole, and well, the minute that in at least one case you see the vertical line failing, the vertical line test failing, well, it's not going to go. All right, it's not going to be it's not going to be a function. So not a function. All right, so not a function here. All right, how about you guys try this one and see what you get? Maybe you did it at home, maybe not. If you didn't do it at home. Okay, take a couple minutes and see what you get for this one. It's going forever, right? Oh, okay, so now if we got the right, so the arrow is indicating exactly. Oh yes, there's one. All right, let's see. This one could be a little tricky, this one. That's because, well, okay, again, let's do this dashed lines for the smallest value of x. However, the fact that we have this arrow right here, and in that arrow is stopped. It stops at 4. Well, I noticed some of you has the 4 as the upper end point. That could be a little bit misleading. However, keep in mind that this is an arrow that indicates it's going on forever. So in this case, what we want to do here is domain using interval notation. That's our smallest value of x, which in this case, what's the smallest value? -5. -5. Now, be careful because we did a bunch of finding domains involving arrows. Some of them were about diagonal lines or curves, like the one on those in those cases, we broke up those arrows into two directions to indicate that a function is going to positive infinity in the horizontal and the vertical direction, or towards the bottom, depending on how the graph and how the trend looks like. However, in this case, it's totally flat, so it's just going all the way to infinity. All right? And let me write the range, and then we will take care of the set builder notation. Yeah, we're going to work on that one later. Now, again, to find the range of a function from the graph, recall that we scan the graph from bottom to top. That is, we go from the smallest value all the way to y to all the way to the largest value of x. And again, if it works for you, the window that gives you those limits. I mean, in the cases where we don't have arrows, like in this case, it just goes between, what are the values? -4 all the way to? -2. All the way to -2. So -4. Whoops, different color. -4 to -2. And in both cases, brackets, right? Because we can see all solid values. If we had something like an open circle here, well, in that case, that we are not including that value. Well, that's actually going to be something like this is going to be on the next example. Let's write this using set builder notation. Again, recall that last time we were playing between interval notation and also set builder notation. For set builder notation, all we do is write an inequality. Well, this -5 to infinity, that is, it's all the numbers that are greater than, and in this case, or equal. So let's just write that as an inequality, x greater than or equal to -5. All right? And well, for intervals where we don't have an infinity involved, recall that all it takes to write it as an inequality, and again, careful with the notation here because this time is a y. Y such that, well, let's write the numbers, -4, -2, and I'm going to make a silly mistake on purpose so to see if you can catch it. Do we all agree with this result? What's wrong with it? Is the inequality symbol, what do I need to change to those inequality symbols? The equal, right? The equal, all right? Because again, we have solid points, not open circle. Actually, let me erase this bubble here, all right? Domain or, function or not a function? Function, all right? So that's a function. I'll let you work on the next one. And although that's the last on the handout, yesterday when I was assigning the homework, it came, some kinds of graphs came to my mind that I would like to do something like those. So when you do them on the homework, at least you're familiar with some cases, all right? So I'll give you a couple of minutes to work on the last one, unless some of you did it for homework. So we are looking at finding the domain and range for this graph, right? So let's see. Domain and range. All right. Oh, but before writing any interval or any inequality or anything, well, again, we have this arrow, but this time the arrow is going in a diagonal direction. That means that breaks up into two essential directions. So let's go ahead and do that. Well, this arrow is indicating that the function values go to the right and then up. So I'm going to draw an arrow pointing to the right and then pointing up. From here, well, we can already have an idea of what the domain of this graph will be. This function represented by the graph will be. Well, notice this time we have this open circles, and that open circle, well, in the x direction, which is the smallest value of x, so it takes the value of 2 this time. So, okay, so that's 2. However, this time we're not going to use the brackets. We're going to use the parentheses because of the open circle, because it's exclusive this time. Yes? Negative. Negative. Yep. Comma, well, again, we're going to scan the graph from left to right, but this arrow is indicating the graph goes on forever in the x direction. That is, it's going to be represented by infinity. All right? And then the range, we're going to scan the graph from bottom to top this time. And that means that's going to go between also -2. Scan the graph from bottom to top, like a camera, and it's going to go up in the direction of the arrow. Well, again, the arrow here is indicating that it's going to go to positive infinity. It's also -2 to infinity. Now, interpreting these intervals again, -2 to infinity means all the values of x that are greater than -2, but in this case, just greater than -2, not greater than or equal. We don't have the equal part because we have the open circle. Another way to interpret this, well, it's approaching to -2, but actually never getting to 2. Negative 2 rather, could be negative 1.9, negative 1.99, negative 1.999, many decimals from 9, but never exactly negative 2. So using set builder notation, that's x greater than negative 2. All right, just greater than, not greater than or equal, and same for y. That's y greater than negative 2. All right.
Can you get this correct if you switch it negative 2 less than
2, okay. Negative 2 less than y, do you mean?
Actually,
Like-
both of them, if we just flop it.
Like this?
Yeah.
I mean, logically it's correct. However, it's a little bit weird to read. When it comes to inequalities, I mean, it's fine. However, typically we read, okay, what are we talking about? About the y's. And then what about the greater than or less than, greater than or equal, less than or equal. It's not, this statement is not incorrect because you are doing the logical equivalent. So either I would take it correct. But we are more used, when it comes to equations and inequalities, we are used to have our variable on the left side and the number on the right hand side.
Okay.
Yep. What would be incorrect though is if we do this, have that inequality sign like this, because it's no longer the same meaning, right? For example, 3 is less than 4, right? And we can also say that 4 is greater than 3. That's still logical. However, is 4 less than 3? Not in this case, right? And here, that's what we have. In this case, this is correct, right? Let me erase this one. Okay, so you might want to use the back side of the page for other examples I'm going to make up here. So, let's see. I would like to do, how about something that looks like 1, 2, 3, 1, 2, 3, 4. Okay, I'm going to do this sort of, okay, sort of a V-shaped graph upside down. And let's have a look at this one. All right, looks a little bit more complex. However, we're going to look at graphs that will look like this later when we get to the graphs of trigonometric functions, in particular when we get to the graphs of secant and cosecant, which have like wave-looking shapes up and down, upside down and pointing up. And well, we're gonna have like these gaps right here. All right, so this is what we're going to do. So, again, I would like to break up. This these arrows in the correct directions, to the left, up, and then down, down, to the right, and to the left. All right? So, let's see. So, scanning the graph from left to right for the domain, I think this one is not going to be a big issue, despite we have graph at the top and at the bottom of the on the same grid. So here, when we look at the graph from left to right, all right, we don't see any gaps or any holes or any discontinuities, you know. So for this one, the domain, it's going to be all real numbers, so negative infinity to positive infinity, and using set builder notation, x such that x belongs to the set of all real numbers. All right. However, it is the range that I'm a little worried about. Okay. All right, range. For the range, okay. So when we scan the graph from bottom to top, check these arrows pointing all the way down to negative infinity. Well, that indicates we're coming from negative infinity. However, we're going to reach a maximum value. However, did you notice that there's no function values in between this cusp and that cusp? So the graph is empty in between those two V-shaped graphs. All right. So okay, how do we describe them? Well, in this case, we have to list two interval notations. So one for the graph at the bottom and another one for the graph at the top. Okay. So the first one indicates that it's coming from negative infinity. And it's reaching a maximum value of, what's that, 1, 2, 3, negative 4? Okay, negative 4. And with a bracket here, by the way, because it's including the same value. All right, and then what are we going to do? We're going, from here, we have to jump to the other cusp. That's going to be our new lowest value, which, by the way, is 3. And it's going to go all the way up to positive infinity. And in this case, for the 3, it's also inclusive because at this cusp right here, we have a solid point. Now, the correct way to put these two together is by using a union symbol. You may have seen this union symbol before. Looks like an uppercase U. It's kind of a stylized U, so that's to connect. So that's the union of two sets that together comprise the whole, well, in this case, the whole range of a function. All right. Now you might wonder, how do we express this using set builder notation? Well, number one, whenever you have something more composite, something more elaborate like this, my advice, express these two as separate inequalities. I'm going to write them below. So negative infinity to negative 4, that means in this case, well, careful, it's not x, it's going to be y. It's going to be around y and the negative 4. However, the fact that it's going away to the negative infinity, it means less than or equal to 4, the negative 4, right? That's what this interval notation means. 3 to infinity means 3, 4, 5, 6, 7, 8. That is all the numbers that are greater than or equal to 3. So in this case, y greater than or equal to 3. Now, when it comes to what's it called, the x, oh no, not x, it's y, such that literally copy and paste these two inequalities, just separate them by commas. Y less than or equal to negative 4, comma, y greater than or equal to 3. All right? So essentially we will be putting them together. And this kind of idea that we're doing here, actually we're going to get to that more in depth when we look at the compound inequalities, which is the handout I gave you today, the other one. All right. Now, function or not a function? Not a function, right? So not a function. All right. There's one more I would like to make up. One that it's even going to give you, it's going to introduce you rather to a whole new term, right? Okay, so let me do another Cartesian plane. Okay, and let me do a horizontal line. And that horizontal line, it's going to be at 1, 2, and 3. All right, 1, 2, and 3. Okay. When it comes to the domain, okay, domain. I think the domain is pretty straightforward by just looking at this horizontal line with arrows pointing on both directions, right? So it looks like it's all real numbers, right? Negative infinity to positive infinity. All right? And using set Bueller notation, that's x such that x belongs to all the real numbers. Okay, the tricky part right here will be the range. Okay, so what did we do again for the domain? For the domain, we scanned the graph from left to right, and I mean it's pretty easy to see that it's going to come from negative infinity and it's going to go all the way to positive infinity. Now, what about the range? For the range, we will have a very limited panning to go from bottom to top, right? In fact, how many values are we going to be allowed to get when we scan from bottom to top? One value, right? And what is that one value? 3. Okay, this is going to be new terminology and new way to describe it. Actually, there's only one way. There's no interval notation for this. So range, the range, we just use curly braces and write down the number 3 inside. That's the only value that the function takes. Well, this special notation, which is only one single number inside the curly braces, has a special name. What is the name of that? Well, it's not an interval, it's not a set. Well, technically it's a set. It's a set of values, well, comprised by one single value, but in this case this is called a singleton. Singleton.
There's no zero anywhere.
No, there's no zero in this case because it's not going. Good question. It's not going from like 0 to 3, for example, or from -4 to 5, for example. No, it's just 3 because the y value for this horizontal line, it's always 3 regardless of your value of x. For x equals 1, what's the y value? 3. For x equals to 7, the y value also 3. For your favorite value of x, you will get that value of y equals to 3. That's why we call it a singleton in this case, right? Maybe, have you ever heard of those singletons before? Maybe not, right? It's a new terminology that we're going to use in here. All right. Let's see. Is there anything else? I think we're fine for this handout.